Hello, we are Memphis University, and today we are doing another calculus done wrong lesson where we wrong calculus before calculus wrongs us. And today what we're going to be doing is we're going to be hanging out with our new pals integrals. Today it's going to be nice and breezy, I believe. You can't rush friendship, of course, so let's just talk about integrals, sort of explore our relationship with integrals more. And today what we're going to be doing, if I can open this pen, which I might not be able to. So what we're going to be doing is we're going to talk about integrals as area under the curve. So integrals as area. So eventually we're going to be taking integrals with antiderivatives in the fundamental theorem of calculus, but in the back of your mind you should always think of integrals as area under the curve, as a limit sum that we talked about previously in our last video. Just like when you're thinking about derivatives, just in the back of your mind you're thinking about derivatives as slope. So let's talk about integrals as area under the curve. So I have a little integral here, a to b, f of x dx. Again, just be familiar that the dx and the integral are always a pair. So you have the integral of f of x. So again, what this means is that this is the area of between a and b, between those x values a and b. So between, let's write it differently, friends. So let's talk about the function first. So the integral, this by definition is the area between the function and the x-axis. Let's write that first. So it's between f of x and the x-axis. And then how does a and b go? Well, it's going to be on that integral, so on a to b. I'm really bad with prepositions today. Let's write from instead. From x is equal to a to x is equal to b. So it's not going to be too bad. So today we're going to be doing a little bit of geometry. Hopefully you like geometry. I'm not the biggest fan, but the geometry should be pretty simple. Knowing the area of rectangles, base times height, knowing the area of triangles, 1/2 base times height, knowing the area of circles, pi r squared. So we will be able to sort of have these graphs, and then what's going to happen is we're going to find the area between our functions and the x-axis. So before we get started, the only thing you need to remember slightly is that negative area. Let's talk about negative area real quick. So if you have area, we're going to have the function, but the function is going to be crossing the x-axis eventually. So if the function is above the x-axis, let me draw a little picture here. So let's say our function looks like this. So here's the x-axis, here's our function. So just keep in mind that we're trying to find the area between the function and the x-axis. So notice we're going to be finding this area right here. I'm going to call that area A, and then you're going to be finding this area B, because again, it's between the function and the x-axis, the function and the x-axis. Sometimes some students try to find somehow this area, maybe like trying to have some sort of line here, but this is not part of the answer, because notice that this is not in between the function and the x-axis. So why I'm drawing this is that we do need to focus on negative area. Basically, if you notice that sometimes the function is above the x-axis, sometimes of course it's below. Anytime it's below, that's considered negative area. So this is just a caveat, if you know some Latin. This is the area below the x-axis is considered negative. So for example, for this guy right here, if this is little a and little b, kind of confusing that we're using the same letters, but if this is little a, little b, this is big A, big B, that means that this integral would be the area of big A minus the area of b, as we'll see, because b again is considered negative. So this shouldn't be too bad. We're going to be finding areas. We just have to be a little bit careful about negatives, and then also we should know our geometry formulas, our geometric formulas. So let's get started. Again, this is not too bad. We're going to first start off with two practice examples where the function is explicitly said. Those are actually going to be a little bit harder because we're going to have to draw the graphs ourselves. And then what we're going to do is we're going to do questions on a generic function f where f is not defined, but we do have a graph of f, and that's actually more realistic. as you'll see when we do, as you take like AP Calc or college exams and things like that. So let's erase this. So first one is going to be actually the trickiest one. So we got this. So let's do this integral real quick. So it's going to be the integral from -3 to 3 of the square root of 9 minus x squared. So this is actually a pretty tricky integral because it's hard to know what this picture is. I do have my dx here. So let me remind you, actually, I believe of algebra 1. So remember that the area of or the formula for a circle from algebra 1 is x squared plus y squared is equal to r squared. So x squared plus y squared. I'm going to call this 3 squared. 9, of course, is 3 squared. Notice that if I sort of isolate y here, I'm going to get y squared equals 9 minus x squared. And then to isolate the the y itself, I'm going to take the square root of both sides. So it's y is equal to plus or minus the square root of 9 minus x squared. So notice that we do have to choose plus or minus. So when we have this function actually isn't a circle. It's actually a semicircle. I don't know how to pronounce that word. I'm not sure if it's semicircle or semicircle. So I'm going to alternate just to make sure that I'm at least half the time right. So in this case, what we're going to be graphing is the top semicircle of our function. So I can draw it real quick for you guys. So, -3 to 3. And this is the picture. So if we had the entire circle, the plus or the minus part, we would draw the entire circle. But in this case, because we have the positive version, we just draw the positive side, the top part in the first 2 quadrants. So this integral, again, is pretty tricky. This is really the best way to do this integral. In the future, we will be knowing how to do, or we will know how to do antiderivatives. And once we know how to do antiderivatives, for a lot of these functions, for the next one, for example, you'll be able to evaluate the integral without drawing a picture. But in this case, for these sort of format questions, let me just write the general. It'd be the square root of r squared minus x squared dx from certain numbers, usually -r to r or 0 to r maybe. That'd be a quarter circle. So if you have these guys right here, you just need to recognize that these are semicircles. So what's the answer to this question? Well, again, what we're going to be doing is we're going to be finding the area of this semicircle. And so the semicircle is just half of a circle. This area of a circle you already are very familiar with, of course. It's pi r squared. So then that's the area of a full circle. So what's the area of a half circle, a semicircle? Well, that's going to be pi r squared divided by 2. Just take this bad boy, divide it by 2, have it, and we should be good to go. So we're actually almost done with this question. Notice I am finding the area from -3 to 3. That's what these numbers are for. If we were going 0 to 3, we would just be doing this quarter circle in the first quadrant. So we would be divided by 4. But in this case, we have the semicircle. So it's going to be 9 pi divided by 2, because we plug in r for 3, so it's 3 squared, which is 9. So again, not the hardest question if you can recognize that it is a semicircle, but if you try to evaluate this using U substitutions in the future, or even the fundamental theorem of calculus, you're going to get stuck really quickly. So it's just nice to have this in the back of your mind, kind of a rare integral, but this is the best way to do it. So the main point of this was, of course, to illustrate that to evaluate this integral, we're finding this area. Maybe I should have shaded it in. We're finding this area, which was just pi r squared divided by 2. Because it was the area of this semicircle. So area of semicircle with radius 3. So that's that. Now let's move on. Let's try a different sort of question, something that involves rectangles and triangles. So I'm going to erase this guy. So let's just go straight to the hardest question. Let's try to do a piecewise function. Because we are bold, we are strong, we are brave, we can do this too, we can do this. So my next function is going to be f of x equals, and piecewise functions, you get to draw fun little swirls like that, squiggly lines. So my function is going to be 5 for x smaller than 2. And then my next function on the other side, it's going to be x minus 3, 4x bigger than 2. So I don't know if this will work, but we might as well try. So what I'm going to do is I'm going to try to integrate. So integrate this function, meaning find some areas, of course. And we're going to go from -2 to 5. So this is going to be our guy. So again, today what we're going to do is we are doing integrals by area in order to define area, especially if the function is explicitly said, but the graph is not provided. We unfortunately have to draw the graph so that we can easily compute areas. It's easier to compute the area of a triangle or a rectangle if you can see the triangle or rectangle, of course. So let's try to draw this little guy. It is pretty tricky because it is a piecewise function, but the pieces themselves aren't too bad. So we should be good to go. So I'm going to draw this guy. Hopefully I have enough room. Let's label the axis. Keep in mind that we are going from -2 to 5, so we don't care about the function beyond those 2 points. The limits are very important because it helps you enclose your area. So I have -1 here, -2. We have 1, 2, 3, 4, 5, like so. So piecewise functions do intimidate students because there's multiple parts of them and people don't like things with different things. But keep in mind that anytime you have piecewise functions, just tackle each piece individually. So I'm going to first draw this function and then I'm going to draw this function. So I have f of x equals 5 for everything from -2 to 2. So the function 5 is actually pretty simple. It's just a horizontal line. Y is equal to 5. So we have 1, 2, 3, 4, 5. Nothing really to say about that. Oh no, look at our problem. This is the worst drawing ever. And the only thing I'm drawing is the y-axis here, so it should be a little bit more smooth than this. Let me quickly draw these guys right here. So hopefully you can tell that this is the y-axis. It's not my prettiest y-axis ever, but again, what this function looks like from -2, because we're starting off with the left point, hitting what I call the split point of the piecewise function, meaning where the piecewise function diverges into a different function. So in this case, we're going to go -2 to 5, and then we're going to dot this, and we're going to go down to 2. So this is the function. Cool. We'll draw those lines later. So now what we need to do is we need to draw the other function. So if you recognize the other function, that is a line, not too bad, but we do have to draw a line. It's been a while since you've drawn lines or been required to draw lines. There's multiple ways to do this, of course. You can start off with the x-axis, things like that. You can start off with the x-intercept. You can do slope things. You can draw 1 point. But in my opinion, for these questions, especially for the practice that we're about to do, the best way to draw this line is because we have 2 x values, we're going to have the 2 point because that's from the split point, and also the 5. Let's just plug those 2 guys in, and then what's going to happen is we are going to connect those dots. So when you plug in 2, you're going to get 2 minus 3, which is -1. So it looks like we have the point 2, -1. And then when you plug in 5, you're going to get 5 minus 3, that's 2. So that's going to be right here. This is not going to be the greatest picture. My students tell me I'm not the greatest artist in the world, but I'm like the 4th greatest. And sometimes being the 4th greatest means that you still mess up. So that's my line. Wow, this is the ugliest thing in the world. But hopefully you can see what's going on. Let's draw like this. Let's be more confident in our line. Always nice to just change the point here, change the point. So again, if you ever have a line and you want to draw that graph, because you know sort of what points you want to go from, and in this case we're starting with the split point going to the end point of 5, those are the 2 points you want to do, and then just draw that point. Draw that line by connecting those 2 points. Keep in mind that the x-intercept is important. You want to draw that accurately, and in this case the x-intercept is 3. So now we are ready to find the integral. So we've drawn the picture, that was the hard part. Now we're finding the integral. So notice what we want to do first is we want to be very careful in determining what area we want to find, because again, this is practice. This is the first time we're seeing this. So we want to be careful about what area we want to find. And what I'm going to advise you guys is that a lot of times in these questions, you can break up this area into smaller pieces. This is just a nice life skill. You have a problem, you don't want to deal with a problem in your life. So what you do is you break it up into smaller portions, and then you deal with each portion individually. And then at the very end, you sort of encapsulate your results, and then you should be able to find the solution to the original problem. Nice life skills in a calculus lesson. So in this case, notice we are trying to find the area of various regions. What we need to do is be careful about what regions we're going to find. So the first one is from -2 to 2, and it's between the function and the x-axis. So it looks like this guy is just a rectangle, as so. And then what we're going to do is we are going to find the area afterwards. It looks like we have 2 triangles here. So hopefully you can see the 2 triangles. This triangle right here, this small little guy right here, and then also this triangle above the x-axis. Again, it's always the area between the function and the x-axis. So again, you're not going to be finding this area right here. Sometimes my students are tempted to find this area or this area, but it's not in between the function and the x-axis. So now we are ready to do this. We are ready to answer the question finally, probably taking a lot more time than we actually needed. But just look at this guy right here. The smaller one is the one that you want to be wary of because this is below the x-axis. So it's going to be this positive rectangle area, this positive triangle area, and then minus this little triangle right here. So as you get accustomed to this, you will get very familiar with this, and you will be finding areas below the x-axis as negative. You're just going to consider them negative sort of off the bat here. So let's finish this question. So let's find the area of these 3 things, and then let's just add them up. So the area of this rectangle is just base times height. So it's 1, 2, 3, 4 for the base, and it's 5 tall. So it looks like it's going to be 4 times 5. That's the area of this base. Then again, we have this little triangle, but it's negative area because it's under the x-axis. Just remember that, and you should be good to go for this lesson. So in this case, it's going to be 1 times 1, base times height divided by 2, where the base and the height were both 1. And then this guy, this little rectangle, it looks like the base and the height are both 2. We have 2 isosceles right triangles, doesn't really matter. So we're going to write 2 times 2 divided by 2. And then again, we finished our things. We took every single piece individually, every single area, and now we're ready to find the final answer. Looks like it's going to be 20 minus 1/2 plus, and then these 2's cancel, so 22. 2 added to the 20 is 22, minus 1/2, I think that's going to be 21.5. You could write this as a fraction. Please don't write this as a mixed number because mixed numbers are only for like 5th graders and bakers. But again, for this question, and you probably won't do this question actually, this method once you go past this lesson because you'll be able to know how to do antiderivatives, but this is always a backup option. And when the function is not drawn for you, you draw the function as shown, and then what you do is you find the area of these individual pieces, keeping in mind that the area under the x-axis is considered negative. So again, we will have a much more powerful tool in the future, which is just antiderivatives, so we won't have to draw these graphs because people hate drawing graphs. I hate drawing graphs. So this lesson is actually more important in the following example when it's a generic function and you have the graph of the function already provided, so you don't have to do anything, and you're going to just find the areas. And these occur on graph free response questions on the AP exam and also in college exams. So what we're going to be doing is we're going to be finding some areas in this case of a graph already provided. So the next fun thing is we're going to just draw a generic graph. Let's just draw something pretty simple. Let's draw this. So we have this. Let's see, what do I want? What do I want? So many choices. So I'm going to draw 1, 2, 3. I'm going to be a little bit complicated. 1, 2, 3. Then what do I want? Let's see here. Let's do a circle. So let's do 4 actually. Just trying to draw this picture. Let's draw a semicircle here. So not the best picture, but hopefully you can tell that this is a semicircle of radius 2, 2, 2, 2. Then on this side, I'm going to go 1, 2, cross this out, do another 2. So this should be at -1, -2. And then I'm going to just finish this off with a rectangle. Not super inspiring. 1, 2, 3, 4. Let's just do 5, 6, 7. And then over here, let's just cross it again. So we're going to cross it. Let's cross it at the very next point. So this would be 2, and then it should be -2 as well. So this is my generic graph of f. Hopefully you like my art. I'm going to submit this to some various museums. So we have this, and what we're going to do is we're going to find some integral values for this function f using this picture and finding areas. So let's get started. Let's do something fairly simple at first. Let's find the area of f from, let's say 1, 2, 3, 4, 5, 6, 7. Let's do -7 to 0. That shouldn't be too bad. So just keep in mind that when we're doing this, we're going to do various questions on just this graph. So just keep in mind that the numbers are very important. You're never always finding the entire area unless you're going for the entire area. These two numbers tell you how much area to do. You don't want to do too much area or too little area, and that's why you missed the question. Because missing the question, while is not the worst thing in the world, is something we would like to avoid probably. So in this case, what we're going to do is we're going to find the area from -7 to 0. So again, keep in mind that it's always in between the function and the x-axis. So it looks like we're trying to find this area. I'm not going to shade it in because I might make the picture uncluttered, and I want to keep my masterpiece intact. But we're going to be finding this area right here, and then this area right here. This area is going to be negative because it's underneath the x-axis, and this area is positive. So there's various ways to do this. The first thing that we have is a trapezoid. And you can do the trapezoid formula, but I don't like the trapezoid formula. So one hint is that you can always break up trapezoids into rectangles and triangles. So notice if I drop an altitude here, I have a rectangle now, a triangle now, and then a triangle. So that's what I'm going to do. So let's find the area of this rectangle first, keeping in mind that it is negative because it's underneath the x-axis. So it's going to be 1, 2, 3 times 2 because it goes down 2. But it's negative, so it's going to be -3 times 2. We can evaluate that later. This triangle has 2 and 2. Not very inspiring, my triangles today, because they're all isosceles right triangles, but what are you going to do? So it's going to be -2 times 2 over 2. So 2 times 2 over 2. And then this one looks like it's also 2 and 2, so it's going to be 2 times 2 over 2. As so. And then what we're going to do is we're just going to add up these 3 numbers. Notice that these 2 triangles cancel, so as you're doing these areas, especially when there's a lot of triangles involved, and you see one is positive, one is negative, and they already have the same area, you can just cancel them out. So we actually could have been like, oh, this cancels out with this cancels out with this, so we would just be doing this rectangle right here. But if you didn't see that, and you are careful with negatives, you will, of course, get the right answer. However you get the right answer is the best way. Whatever way you take, no matter if you run a marathon, if you run 10 feet, as long as you get there in the end, I'm satisfied with that. So for this guy right here, this answer is -6 because these 2 canceled again, and then this is just -6 from the area of this rectangle. So let's try to find a different area. Let's try to find the area from, let's say, 0. Actually, let's just do one more. Let's be a little bit tricky. Let's find the area from -1 to all the way down to this point right here. 1, 2, 3, 4, 5, 6. So -1 is 6. So this looks pretty intimidating because the shapes aren't very sort of obvious. So again, be wary that just take everything slow and simple, slow and simple, slow and simple. Break up everything as much as possible, and then it should be good to go. So let's just try to break up our region before we find the areas of any shapes. So we're finding the area from -1, all the way down to 6. So it looks like we're going to be finding this area right here, which is a weird shape. Then I'm going to find this wing thing. I'm going to call it a wing. I'm going to find this wing thing, but if I drop an altitude, it looks like the picture isn't incredible, but this guy right here is equal to this guy right here because this is supposed to be symmetrical. And then finally we have 2 little triangles, But notice that this triangle will cancel out with this triangle. So this integral actually is the same thing as the integral from -1 just to 4, because the area from 4 to 6 doesn't contribute to the area because there's a positive triangle that cancels off with a negative triangle and they have the same exact area. So this one was 1 times 2 divided by 2. This is -1 times 2 divided by 2. When you add them together, you can cancel them out. So there are tricks to this sort of game, but again, if you didn't see that, you would still get the right answer if you evaluated the areas correctly. So it looks like to find this area, we just have a positive thing, the area from this guy all the way down to this guy right here. So first off, what I'm going to try to do is I'm going to try to find the area of this guy right here. Again, you can always break up things into triangles or rectangles. In this case, it would be a square. It'd be if you form this little square, and this little you would have this little triangle on top, and then to find the area from here to here. Hopefully, you can see what I'm seeing, sort of motioning. I'm going to outline it for you guys. This area right here, you could break that up into a triangle and a square. But it's nice to practice the trapezoid formula sometimes. So it's going to be the average of the bases times the height. It is a sideways trapezoid, if you can't tell, like this. But the heights are actually right here. Sort of like when we were doing trapezoid or Riemann sums. And then the height is right here. So the base, I don't know if I said that right, but the bases are actually going up and the height is here. But it's not too bad. So notice the bases 1 and 2. So we're going to find the area of this trapezoid. So it's going to be 1 plus 2. 1 plus 2. The average of the bases, the average of two numbers is you add up the two numbers divided by 2. And then you multiply by the height. And in this case, the height is 1. Again, we're sideways. So the height is 1. You could have broken this up as this square plus this little triangle. So now what we need to do is we need to find the area of the weird shape. Let's just write area of the weird shape. So minus, oh, it's actually plus because both of these are positive because we cancel out this negative. So we're trying to find the area of this. So it doesn't look like it's possible because these aren't triangles, but notice that this is a semicircle. So what we have to do is we have to actually be clever. Being clever is the worst, but it's nice when you actually see it. In this case, what we're going to do is we're going to find the area of this rectangle right here. And what we're going to do is we're going to subtract off the area of this semicircle. And we're going to end up with what area we want. So let's do that on the side. So what's the area of this rectangle? Well, it's going to be 1, 2, 3, 4, because it's 2 radii, whatever Latin tells me to do, but it's 2 radii, so it's the radius is each 2, it's the entire diameter, so that's 4, and then the height is just a single radius, so that's 2, so it's going to be 4 times 2, which is 8. Hopefully you can see that this is an 8. And then what's the area of this semicircle? So again, we're finding the area of this rectangle, and we're going to subtract off this area right here, and we're going to end up what we want. This semicircle has area pi r squared divided by 2, just like before. So it's pi r squared divided by 2. And in this case, what is r? The r is 2. So it's going to be pi 2 squared divided by 2. These 2's cancel, so it looks like it's just 2 pi. So we are done. What we're going to do is we're going to take this guy and add it to this area right here. What is this area? It's the area of the rectangle, again, with the semicircle sort of taken off. So it's going to be 8 minus 2 pi. So the answer is 8 minus 2 pi. We can simplify this because we can combine all the things that are pi by itself, and then anything that's not a pi, we can combine. So this is going to be 1 plus 2 is 3 halves from this area of this trapezoid times 1, still 3 halves. 3 halves plus 8. Well, 8 is 16 halves, so it's going to be 3 plus 16, which is 19 halves. And we're going to subtract off 2 pi. And that's the answer. So hopefully that makes sense. Again, this is not too crazy. All we're doing is we're using geometry and area to help us evaluate these integrals.
especially when the graph is already provided. You can't take an antiderivative of a graph. You can't type a graph into a calculator for integrals. So this is the only way that we're going to be able to do it throughout the year, as we have these graph response questions, which are very common on the AP exam, at least one per year. And then remember that it's not too bad. All we're doing is we're finding areas of things. One thing you do want to be wary of, and that you will get very used to very fast, is that the area underneath the x-axis is considered negative. So this was negative, this was negative, this was negative. And then if you're having trouble with finding the area of certain things, remember that it has to be areas of shapes you know. It has to be areas of rectangles, which include squares, also triangles, and semicircles or quarter circles or something like that. So just be wary of that. Try to break everything up as small as possible, and then you should be good to go. So hopefully that makes sense. Hopefully you have some sort of more idea of what integrals are as area. Just like normal, we do have a Girls Teach Calculus video. I will link it in the description below, where one of my former students practices questions like we did for the first two, questions where the functions are explicitly laid out and she graphs those functions very neatly, better than me, of course, and she finds the areas between the function and the x-axis. Then in the second half of that video, what she does is she takes two provided graphs like this and she finds a lot of areas and integrals. Sometimes with absolute value, even sometimes with negative, sometimes when you're scaled areas. So if you want a little bit harder version of this, I would highly recommend that video. That video is probably, well, more informative than this video. But if this video was helpful for you, we would appreciate it, of course, if you did like and subscribe. So in our next video, I believe that we are going to be introducing the most important thing in calculus. We are going to be introducing the fundamental theorem of calculus. So be on the lookout for that. Thanks again for watching, just like normal, and good luck as you find areas to evaluate integrals. Thanks again for watching.